Okay, so good morning, everyone. I'm Siddharth, and today I don't know why I'm introducing myself, but today I'll be presenting about Parallelized Gaussian Accelerated MD or ParGaMD, which is one of the recent methods that have been developed through the OnLab. So essentially, the funding for developing this method has come from uh, Shirley's grant that came from Duke Center for HIV Structural Biology. And the aim is actually to use this methods to study the HIV virus. And because MD can act as computational microscopes, ParGaMD becomes a very good method in order to study much larger systems, which requires generally a very long compute time and vault time too. So I think I'll skip this slide. We all know why we need enhanced sampling methods. We all know what Gaussian molecular GAMD is. We all know what weighted ensemble method is. Huh? I just picked this up from the Duke talk that I'd given. So there nobody knew what that is. So yeah. So GAMD essentially, so now I think this is a good slide to basically motivate why ParGAMD is important. So GAMD gives an efficient exploration of the free energy landscape because we add bias potential. So we are essentially like forcing the system out of its lower energy states, and in that way we are able to access the transition states better. But the problem with GAMD is that because GAMD is directly integrated into the Amber system, and Amber does not scale well with GPUs, for much larger systems such as alpha-synuclein that Celeste is working on, or on the systems that Path is working on, running GAMD on one single GPU generally takes no 7 days, 8 days, right? It takes a lot of time, and basically that time and the scaling with GPUs can be mitigated by weighted ensemble method because weighted ensemble method has an excellent parallelization with GPUs, but because WE doesn't have a bias potential, the exploration of the free energy landscape is very inefficient, and generally, even though there is excellent parallelization with GPUs, we need to run it for an insanely amount of high simulation time in order to recreate a free energy surface. So this is where a potential solution where we basically marry the efficient exploration of GAMD with the parallelization of WE, which forms a hybrid method called as parallelized GAMD method or ParGAMD. So the working of ParGAMD is very simple. So what we do is we first run a short MD simulation. Uh, I will correct that. A short MD simulation where we determine the standard GAMD parameters and then, sorry, 2 nanoseconds. I mean, I did 2 nanoseconds for Chignolan. It's a small system. No, you can change it. Uh, not necessarily. I think it's more system dependent because Chignolan is a small system, so you don't need more than 2 nanoseconds. Whereas if you are working with bigger systems, you might need a longer run to get more definitive statistics. GAMD already does that, right? No, the initial GAMD run does that already. Well, I mean, I think that how long you want to run it is really like system dependent, to be honest. Because again, as as I'm saying, bigger the system, better the statistics you want on the system size and understanding of the system. Yeah, yeah. I think you already do that in your standard GAMD simulations when you run NTCMD and NTEB. Yeah. So that gives you, if that is longer, then that will give you an initial a better initial statistics. which determines your GAMD parameters. So generally, if it is GAMD, we we just directly start running the. Yeah, I'm fine. Something got stuck in my throat. Thank you. Thank you. So generally, when we run GAMD, after getting the initial statistics, we directly start the MD simulation with the GAMD potential added. But here, we'll define we need two CVs. I think the only difference between ParGaMD and GAMD is ParGaMD does require CV or CVs, depending upon how many you want to give. So based on the CVs that you give, you define the bins, you set the progress coordinates, and then and the last three steps are essentially the W running with the GAMD simulation in it. Instead of running MD simulations in a W framework that is generally done in WE, we are running GAMD simulations within the W framework. That's the only difference between ParGaMD and WE. But and so because the first thing that we wanted to test was the speed statistics. How fast is it? Definitely, it is very fast. Like I think it's not as fast as W because we are computing and generating additional files. We are generating a gamd.log file in addition to that. So that's why it is slightly slower. But still, you can see that compared to GAMD on one GPU, when we run ParGAMD on 48 GPUs, I think the speed up is about 40 times, which is an exceptional scale up in terms of speed because we are able to efficiently utilize 48 GPUs and speed up the simulations. But you can see that the molecular time for the same, so the ParGAMD and WE were run for the same number of iterations, 4 walkers and 1,000 iterations, but you were able to see a higher molecular time, almost 300 nanoseconds more in ParGAMD because it had a more efficient exploration of the energy landscape, as I will show that. So this graph basically shows a linear scaling. ParGAMD is scaling almost linearly with respect to the number of GPUs. And this is the free energy progression of ParGAMD. So you can see that. So I think in the GAMDW paper of Shirley and Anand, I think the transition states here, I think you have to run a 40 microsecond simulation, right? So, but the thermodynamics, you were able to get through WE in, I see. So yeah, this is explicit solvent. So this is explicit solvent, and actually we were able to start seeing the transition states occurring after just 300 nanoseconds of ParGAMD, which is like very efficient. And I will compare ParGAMD with GAMD and W in the next slide. But this is the general FES progression, and we can see that more or less from 500 nanoseconds to 7.89 microseconds, the transition states remain. So the identification of the transition states was already done by 500 nanoseconds. And if you compare the same thing with GAMD and WE, yeah, 48. Yeah. No, these are all parts of the same simulation, which was run for I think 7.89 microseconds, and I just took snapshots of the generated system. Yes. So I think 48 GPUs it took a total wall time of 14 hours. And I think this was a 15,000 atom system. So Chigmalin and explicit water. So I also ran a parallel weighted ensemble and GAMD simulation with the same parameters. We can see that weighted ensemble is not good at all, right? And especially when we basically truncate the energies to 5 kilocal per mole, where we actually see the transition states. There's absolutely nothing in weighted ensemble. And in GAMD, you can see that the exploration of the higher RMSD and RG regions are incomplete because the transition states are still not identified after 500 nanoseconds. Whereas if you go back to ParGaMD, by 500 nanoseconds, you are able to get a very good lay of the land. Right? Okay, these are the places where the transition states for Chignolan occur, right? So this essentially shows that and I think the reason why ParGaMD is doing a better job than GAMD is because you have two additional CVs which are guiding your exploration through bins. So your exploration in GAMD is not exactly guided because your bias potential is not exactly, you know, leading to a time-based or an efficient guided exploration. It's more or less very random. Whereas in ParGaMD, through the bins, the CVs are able to guide the GAMD to explore more efficiently. And that is why you're getting a better free energy surface. And when it came to transitions, ParGaMD was able to sample more transitions, both from the folded to the unfolded states of signaling and the unfolded to folded states. And finally, yes, so and we are working. I think I'm working on getting replicates of replica simulations of the same, and Celeste is working on Celeste and Maxon are working on getting the same statistics for alpha synuclein. And we hope that I think once we have established this, ParGaMD can actually be used to study the HIV virus. How they do that, I have no idea. So I won't go into that. So I think if you so you guys can I can share it on the group too, but this is essentially the GitHub where you can actually access it. And with that, I'll go into the demo. So I'll be running the simulate. I think I'll be showing it on TAC. But you can. I think the difference between TSCC and expanse is essentially just the difference in the S batch headers. So you can use it anywhere, right? Oh yeah. How do I do that? Sorry, is it zooming in? Oh, it's going up. Okay, up and down. Okay. Yeah, there is zoom here. Do I need to zoom in more? Yeah. Yeah, now we may have to dim the lights. Yep. So in essence, what you can do is that you need to just make very few changes to the already established or to the already given setup of ParGaMD in order to run it. So basically, you can git clone the repository to your directory, and this is how it might look, except for all the log files. So these are all the west.log files which you will get once you run the simulation. So what you just need to make very few changes. So there is this folder called as CMD where you basically do the initial conventional GAMD simulation. So if you go in, you just need to give the relevant files. I think the PDB file or INPCRD or the palm top and your md.in, which I've named it as md.cmd.in, right? And you have this shell script run cmd.sh, which essentially runs your GAMD simulation. So I think this is pretty simple. To explain, you just all you need to do is just delete all the files except for the md.in except for the md.in and your runmd.sh, which are essentially your run files. Oh, sorry. Oh, no, no, no. Yeah, yeah. Oh, run cmd. Okay. The yeah the I'm just running MD this. This is a payment quota company. Yeah. So you just need to remove all other files except for the run scripts and put your INPC and instead of and you have to give your initial topology files and it will run GAMD for you. You can change the GAMD parameters in MD cmd.in according to how you want it to be. And once that is done, uh, you can go to the common files and here essentially again you have to like put your INPCRD and palm top files here, right? Yeah. Exact same thing that you use for the conventional gambling.
PCRD.
I think it's an alternative to PDB. I mean, I think it's another file type which gives a topology.
Okay. And then your PRM top is your topology.
Topology file, yeah.
If you open the we had the Ansible PCRD, you see.
I think it's I think I
Yeah, so this is coordinate.
no this is
Coordinates and
no this is just a coordinate file. This is an alternative to PDB. So I think this for now this is like a PDB file, not exactly an RST file. If you no if you keep your no if you keep huh? I know, but this I think this was meant to be more as a PDB file. I think because Shirley didn't have a PDB file for Chignol, so she gave an INPCRD to be the reference. Yeah, yeah, yeah. So again, here you so in the common files, you essentially need four files: one reference file, one palm top file, one md.in file, md.in for the GAMD simulation. Where now here the md.in essentially you have to run small GAMD simulation. So we have kept it as 10 picoseconds. So 100 picoseconds. So you can vary it like to maybe how much ever you want. The md.in file and the gamd restart.dat. So I mean the addition of the gamd restart.dat is already automatically done when you run the runw script for you. But these are the four essential files that you need there. And in the B states, again you need a bstate.rst and a bstates.txt file here. So I think bstates.txt generally when you run a simulation you generally need only one bstate at least to test it. So again, through the runw script, it automatically takes the MDRST from the CGAMD simulation that you did and stores it here. So now I'll show the run tag script, the run script for this. Yep. So here you can see that I've given 12 nodes. So 12 nodes and 12 MPI tasks, right? And these are all the batch headers. So you have to basically so before you start, you have to basically install Vespa 2.0 to your mini Conda. I think it is a simple Conda forge install that you can do. And once you do that, you just have to Conda activate it to the run script. These are all the Amber initial commands. These are the Python paths that you have to give. And you can see that here, these two, if you look at these two commands, it is basically I am copying the gamd.restart from the CMD into the common files and the md.rst that we get from the cgamd simulation into your bstate.rst. So this will be done for you. And this is essentially .init.sh which generates the initial folders and all as I will show. And this is assigning again, you don't need to change anything except for here. If you are running on a one GPU only, then you have to basically num GPU per node. You have to change the CUDA visible devices accordingly, like depending on how many GPUs you are using. Otherwise, you don't need to change a single thing in this file. I didn't understand what.
You have to make sure that the GPU node has 4 GPUs on it. They might have like
Oh yeah.
more or less.
Yeah, no, I was thinking they're all using NVIDIA anyway.
Yeah. Yeah. So then I have to do VI. So then there are three important files here. One is the node.sh, the env.sh, and the init.sh. So we'll just go through those files. Sh. So here it basically just creates the files for you. So if you have t-state args, I think for the control W simulation, you can just cancel this out. You don't need it. Like you can just comment it out. That's the only change. And env.sh for ParGaMD. Yeah. Yes. Here, so in the environment.sh, basically env.sh sets the environment for the ParGaMD simulation. Here, you have to basically change the Python path according to the Python path that you have. Otherwise, everything remains the same, or except for the node and this one, the node location. So node location is essentially the directory in which you are doing the simulation. So you can just do pwd on your main directory, and that is the path here that you need to give. So for example, I'm so this folder's name is pargamdexp48 GPU. I gave the path to that, and those are the only two changes you need to make. I don't think you need to make a change in node.sh. Only one thing. If you're running a one GPU simulation, this should be CUDA visible devices only. If it is a multiple GPU simulation, then this should be CUDA visible devices allocated. And the change is because when you go into this particular folder, which is Vespa scripts, you basically have to change this file, which is called runseg.sh, which basically tells uh, how each segment runs. So here you have to basically change this again to the palm top file that you have here, this line. The gamd dot, I think this is pretty common. This won't change. This also won't change. This also won't change. So as long as you're keeping your md.in to be md.in, the file name to be md.in, these both won't change. So now because I'm running, so this cluster of lines, because I'm running a multiple GPU simulation, we need a parallelization. So these lines are there only then. So you can see, so if you can see that this CUDA visible devices allocated is defined only when we are running a multiple GPU simulation here.
Is there a scenario would not want to run multiple?
Yes. So that in that case, you can just remove this. Remove these five lines. So when you're running a one GPU simulation, you can just remove these five lines. So when you're running a multiple GPU simulation, you in the node.sh, you have to define the allocated. You have to basically define it as CUDA visible device allocated. But if you're running a one GPU simulation, you can remove this whole thing. But in the node.sh, instead of CUDA visible devices allocated, it should be CUDA visible devices. That's it. That's the only change. And I'll again vi into, so there's one more file called as get pcord.sh. So here again, you have to basically change it to your input files here, the palm top, the INPCRD. And according to what CVs you're defining, your CV definitions will change. For example, here I'm defining an RMSD and RG. You might want to define some other CVs. So accordingly, you have to change that in both your get pcord. I forgot to mention, even in the run seg, you have to do that. So if you go down here again, you're defining your CVs here. That I think this is through CPP trash. So I think I've gone through everything. Yeah. So once you've made the changes that I've mentioned, then you can just do sbatch run tag.sh, and it will run the whole ParGaMD simulation for you.
For the CV, it has to be.
I'm not sure. Does it have to be a CPU? Yeah.
Um, for Android, I think, Android version, um,
Yeah. So the changes that I've mentioned are the only changes you need to do. I mean, it looks like a long list, but when you actually do it, you will understand that you actually don't need to tamper a lot with the initial setup. And then you can just do sbatch run tacc.sh. I won't run this right now. But when you start running it, you will get these three folders: istates, seglogs, and trad So I'll go into them. So when you go, trad are basically where the trajectories are stored. I ran 1,000 iterations. So there is one folder for 1,000 for each iteration. So let me go into the last iteration. The last iteration had 84 walkers. It starts so the folder naming of walker starts from 0, hence it is like 0 to 83, which means that there are 84 walkers. And I'll go into the last walker, say 83. You can see that you have this seg.log, which is essentially your MD, like your MD.out file, the data files for the RG and RMSG, your gamd.log, right? If you view the gamd.log, you will see that it's only run for peak steps. And basically, when you're done with the simulation and you want to basically reweigh the ParGaMD simulation, I have already created a Python file called data extract.py, which essentially this Python code essentially goes through the walkers, determines the number of iterations, and it loops through all the iterations and basically goes into each and every walker. And after it goes into each and every walker, it basically extracts information from the gamd.log file and the CV, the progress coordinate files that you have. And after that, it basically pastes it into one big file that you find in your home directory, in no normal directory.
The CV files here, find out different CV numbers.
Yes, you have to change that. Yeah. So if instead of RMS, if you're naming instead of RMSD.dat, if you're naming it to be something else, then you need to change the file names. I don't think you need to change the variable names. It doesn't matter because it's only valid till this Python code. And when I first ran the data extract.py directly on my login node crashed because data extract.py, especially for larger simulations, takes a long time. So you essentially have to run it separately and to basically, oh, this is for access, so this for expanse. So so that you don't need to go through that again, I just created another file and saved it with my GitHub where you basically there's only one thing called as Python 3-u data extract.py, and the output is basically printed onto one log.out file. So this log.out file you can like periodically view in order to see whether your data extraction is going well or not. Because generally these runs take more than an hour or so, and more importantly, because I have a because in the loop to get the data, I have a try and except here. So it doesn't immediately give out an error. So if it is not able to do this, it will immediately continue to the next part of the loop. So instead of you realizing that the data extraction was not done after 1.5 hours, after it has gone through all the walkers, you can just immediately see whether I basically put these print commands for you to see whether your data is getting extracted or not. And if it is not, you can just cancel your job, make other changes, and rerun the data extraction. So these are the major components of running a ParGaMD simulation. And if for some reason, especially when you're running on Expand, it is highly likely that your job might require more than 2 days, and it might actually stop. So when that happens, what you have to essentially do is so in this case, suppose your 11th iteration is where it stops, right? You basically have to use this where it basically removes that folder, and you have to comment out the init.sh file. So init.sh file always creates a completely new W simulation. When you basically comment this out, and basically you can just rerun the simulation, and when you rerun the simulation, your folder gets truncated, and after your folder gets truncated, it restarts from the 11th iteration. So that is how you restart your W simulations on Expanse or on any other cluster where there is a time limit and you don't have access to a large number of GPU nodes. In Expanse, it's only 4. You can go only up to 16. In TACC, now it is 16 nodes. But previously, when I was doing the analysis, it was only till 48, like 12 GPU nodes. So I did my analysis till then. And I think I hope that was a good enough demo to have a good
Visualize output.
trajectory. I'm working on that. There is you have to concatenate all the nc.files. not exactly all the nc files. I think what you have to do is that you have to go to the last iteration. There'll be basically 84 trajectories. You have to pick one of them, and there is something called as trace in Vespa tools. So you basically have to trace it back to the very initial iteration, and basically you have to concatenate that whole thing. So I'm working on that. I'm trying to work on that, and I'm trying to make that work on the cluster cut terminal, because the Trat6 file, the Trat6 folder is essentially like around it's around 1 TB or something. So like doing SCP and downloading it and all is not an option. Yeah, that's really complicated. That's why I'm trying to. It's easier to make it work on the terminal rather than downloading it and all.
So just visualizing in the terminal.
Not visualizing in the terminal, like concatenating the trajectory in the terminal. Then the .nc file can be downloaded easily. Right? Because all said and done, .nc file will be some 1 GB or something at max. It won't be like some around 1 TB and all. Not everything. That's what I'm saying. You should not concatenate everything, because every walker has its history, right? So it's not like for one walker, yeah, you can concatenate everything, yeah. It won't give you a very large file, even if it is a netcdf file. Yeah, all tracks. Yeah, this whole folder. So essentially, even for you to like choose and concatenate them, you need to have the whole Trat6 folder, and this whole Trat6 folder is like 1.4 TB or something, which is and that is after me zipping it. So just imagine the original file size. So
I mean, you won't be able to.
no. I meant for SCPing it, basically for copying it out. I meant for copying it out. Yeah. For that, so I tried to, so the zipping took 12 hours, and when I SCP'd that RAT6 file, it did not SCP because it went past a 24-hour limit. It's that big. Yeah, here, yeah. So that's what I'm trying to do, like with regards to concatenation.
That reduces the file size by a lot.
I haven't tried it, but
But that 2.5 terabytes, and I strip it and it's 150 G or 128 or 150 G. So it's like 10% of the original size.
I see.
The
Yeah,
size is
stripping it would help a lot, but yeah, this was particularly such a small system, so I guess
yeah,
it
that's
doesn't
still
even bother.
pretty big for children.
Yeah. Yep. So I think that is it from my side. Other questions?